today we'll have the second half about the hands-on on system level simulation. I think some of them, Professor Jahangir.
No, it would be mostly like microgrid.
Yes.
Designing.
Yes. So whatever you studied in the first half, some of the case study we are going to see in this hands-on program. I think all of you downloaded that course, right? So keep it open and ready, and over to Professor.
Again, I mean, so Dr. Abbas was my PhD student. So he already finished PhD, now working as a postdoc with me. So he has done his PhD on hydrogen-based microgrid planning, designing, and different optimization, cost-benefit analysis. So with that, Abbas, I will hand over you to now. Please start.
Thank you, Professor Jahangir. Okay, today I would like to talk about and show you how we can do the coding and model the microgrid designing, incorporating a wide range of technologies, renewable technologies such as wind, solar, hydro generation, or how we can model different types of energy storage system, incorporating batteries or pumped hydro, as well as also previously we have developed two different tools for the microgrid, two different types of design.
So Abbas,
one is including and considering hydrogen-based technologies to see and compare the cost, the levelized cost of energy, and so forth. And another scenario is that model the microgrid using the existing technology without utilization of hydrogen technologies.
So Abbas, sorry, I mean, still,
Yeah.
I mean, again, I mean, we can't see your that previous. Can you open that MATLAB file? Yes, now it's, I think, better. Yeah, you can talk now. Or maybe you can zoom in, because you can do it here from, I don't know. Full screen, okay.
I zoomed in.
Yeah, please continue.
Therefore, in order to develop the model, because we want to optimize and minimize the total planning costs, incorporating the capital costs and operational costs of the system, so we need to develop an optimization problem. If we want to do coding in MATLAB, we need YALMIP solver.
Abbas,
It is, yes?
can you just make it full screen? I think on the top right corner of the screen.
This one?
No, the screen size, screen. Make it full screen on the top right. Or I don't know whether it's. No, go back MATLAB again.
Don't know how I can.
So you cannot
change
make bigger
this.
than that?
No, there is no option to change the size.
Oh, but did you check on the top right hand corner like a rectangular things?
Do you mean here?
No. Go to MATLAB. Yeah, that one, yes. So I think, yeah, that will not go more than that. But anyway, so yeah, please continue.
Therefore, to solve the optimization problem in MATLAB and do the modeling, we need another toolbox and package, which the name is YALMIP. And Everyone, have you downloaded the YALMIP toolbox or not? I can show you how we can download the YALMIP.
I think they have already downloaded, right? They have already downloaded, so please continue.
Okay. If you go to the YALMIP website, you can download it from here. However, there are some tutorials for them and examples. And if you would like to, you can.
Allow it, no problem, or don't allow it, I think it's.
Yes, you can use it. Using getting started, it will give you how it works, how it is structured. As you can see, there are several functions that are important for us. How we can define decision variables, which we need to use this SDP var, and we need to model constraints, and we need to define objectives and options that allow us to select different types of, for example, solvers. If it is linear programming, we can use different linear programming softwares such as CPLX or GLPK. For the GLPK is an open source solver and CPLX is a commercial solver, as well as non-linear programming solvers. You can install them and also set up in the MATLAB and use it. If we click on SDPUR, you can see here that the method that we can define decision variables is like this in the MATLAB. It shows the dimension of the matrix. For example, we have a output of the generation. We can show it in MATLAB using the arrays or matrices. It can be first dimension, second dimension, and so forth, depending on how you model them in the MATLAB. Therefore, it is very important, and it gives us this website other examples. So next step, after defining constraint and objective that I will show you how we will define it for our microgrid example, you need to optimize it. And if you click on the optimize, you need to use this syntax, optimize. First, you need to put your constraints that you have defined already, and then the objective function. And these options, as I said, it is related to the selection of different solvers and manipulating the settings if your problem is very complicated. Regarding the options, you need to use SDP settings. And here you can see that how you can define and manipulate the settings. You need to use this syntax. And then you have one field and value, and then you can change them. For example, here you can see you need to use solver. They have used mosaic solver, and these are other parameters that you can change it and set it. So you can read the instruction, they have explained it very, very well. So if we get back to the modeling here, there is a folder that incorporates several files, MATLAB files, as well as one input data sheet, which is prepared. Our input data is prepared in the Excel, and we need an output file. Again, it is like we need to prepare our results and the results of our problem in the Excel sheets. So we need to import in MATLAB, import and export. Import the data and give it to the our problem modeling that we will do with YALMIP. And after solving the optimization problem, the results will be went to the output sheets in the Excel. So first we need to click on the input Excel sheet that I have prepared. So in this microgrid design, we want to consider different technologies, as I said, solar, wind, battery, diesel generator, mini hydro generator, pumped hydro storage, and we have the hydrogen technologies. However, in this example, we don't consider hydrogen because this example is not hydrogen-based microgrid design. And this one is the utility or the substation that sends electricity and supply all demands in the microgrid. So we have defined the indexes for them. We gave them index from 1 to 8. Then in another sheet, we can see some input parameters relating to the generators. Again, in one column, we can see technology type. Again, 1, 2, 3, 4 to 8, which are these technologies. We have used that numbers for solar, wind. They are important for us because in the coding in the MATLAB, we need to refer to these technologies. And another important parameter is existing installed capacity in the network. Therefore, this Devon Bridge microgrid, there was only the utility that was supporting the electricity. However, they would like to plan for the next 25 years which type of technology would be cost effective to install in that area. Therefore, we need to go for optimal sizing for different types of technologies. And another input parameters that we need to consider in our objective function, because we want to minimize the operational costs and the capital costs. One is variable operation and maintenance costs for each technology. Again, we will give them some index because we want to use them. And another one is fixed operation and maintenance costs parameters. And another one is fixed costs for them, fuel costs for different technologies. We have only considered 1, 2, and 3 indexes. What does it mean? For example, what does 1 mean? 1 means that they don't need any fuel because solar, wind, or battery or mini hydro, they don't use fuel. They are using, for example, natural fuel, not fossil fuel. However, diesel generator, they use, for example, fuel or also hydrogen, they need hydrogen fuel. So we have defined 3 different fuels to make a difference between them. And maximum install capacity index, again, similar to technology type index, we will define it. And another input parameters is maximum building rate or construction rate for each technology, because we want to construct the technologies over the 25 years. For example, in the second year, we need to install 20 kilowatts of wind turbines. However, in the next year, we need to, or next 5 years, we need to install another, for example, 30 kilowatts. And we have a reliability factor that shows that, for example, if the microgrid wants to move from grid connected mode to isolated mode due to faults or any reliability issues in the system or any events that may happen, we need to, in emergency situations, we are required to, for example, maintain, for example, 80% of the loads as emergency loads or 50% of the loads. So it will define this factor for them. And we have also maximum capacity factor for renewable technologies and generation, and load factoring, discharge efficiency. This is for storage systems, as you can see. We have defined it only for battery and pumped hydro because they are the only storage systems. So this is the discharging efficiency, and this one is charging efficiency for these 2 types of technologies. And this is the energy storage system rate. For example, it shows that how long does it take that, for example, battery completely charged or discharged, as well as the pump hydro. We have considered 2 hours battery and 8 hours pumped hydro. And another important parameter is demand, the electricity demand that each load has, and in our microgrid includes, because we would like to plan and design the microgrid for the next 25 years. And we want to do the analysis on the quarterly basis. So we need to define 4 quarters, quarter 1 or season 1, which includes 24 hours. We consider 1 day or 24 hours as a representative of other days in the first quarter. Same again, another day for second quarter. And quarter number 3, and at then quarter number 4. So we have considered 4 seasons in the in our problem and model. Therefore, as you can see, we want the start of the planning project is 2022, and for the next 25 years, it will go to the, we have defined it until 2050. However, we will consider only 25 years, if I'm not mistaken, only this one or this one, this row works for us in the problem. We have considered fixed values for each years. However, this is like the base load for the 2023. However, because we have a load growth, we need to multiply it by a factor to show the effect of different items like population growth, something like this, because our load will increase year by year. To show that trends, yes, here we can see the multipliers. As you can see here, we have defined several 5 scenarios. However, we will consider first scenario in this example. As you can see, they are increasing, the multiplier, they are increasing, and it shows the load grow, the trend of the load for the existing substation. In addition to demand, another parameter which is variable is like solar output power. Again, we have modeled the trend for it based on the maximum capacity of the solar system. We have calculated them based on the irradiation and temperature information of that area. So we have considered all of them. For each year, we have considered them. Again, first quarter data is different from other quarters. As you can see. And similarly, for the wind turbines, because the wind speed is different over the 24 hours of a day. Therefore, we have calculated them. Another important thing that you should note is that we have normalized them, and it is like we converted them like to the multiplier or factors. It means that when you find the optimal sizing for technology to show their impacts on the scheduling of, for example, wind turbine solar PV system, we need to multiply them by the maximum size of the technology that we will solve. And also I told you that am I connected? Can you hear me?
Yes, we can hear you.
Oh, okay.
So Abbas, just
Pardon?
just ask them whether they have got any question.
Yeah. Do you have any questions so far?
Yes, any questions? You can mute, sir.
So no question?
No question, right? Okay.
Please continue.
Okay. Now we have defined the demand data and renewable energy sources data in this sheet. And then another parameter is variation and operational maintenance costs. In this example, we have considered 0 for the variable operation and maintenance costs for different technologies. However, we have defined them in the fixed operation and maintenance costs. You can use these values. And here you can see feed-in tariff data, because the microgrid is when it is in the grid connected mode, it can sell electricity to the upstream network. Therefore, we need to use feed-in tariffs for the microgrid. This is the price of electricity which is sold to the network. Again, we have used the data for different quarters. And another one is consumption tariff that we can see, in the bills. So what would be the consumption tariff structure? The structure that we have used is based on two values, off-peak and peak values. This shows the price of electricity for off-peak periods and peak period. And here we have the fixed operational and maintenance cost. When we install each technology, the total cost of, for example, main operation and maintenance cost for each technology is equal to these prices multiplied by the size of technology that we would like to find in an optimum way. Here you can see that the maintenance cost price, for example, for solar is cheaper than wind. However, compared to mini hydro and pump hydro, we can see this one is cheaper than the other. So all these information, they are very important for us because we need to use all of them in our modeling. And this one is capital cost. The capital cost, again, for each technology, is based on dollar per kilowatt. And we have used the prices for each technology. And we can see that the prices are reducing by year and year because of their maturity. So we have considered also this uncertainty in our model, the capital cost of technologies. If you see, we can understand that, for example, battery is cheaper, mini hydro compared to other technologies is this price is very less compared to other technologies. The most expensive one is hydrogen. So it can make a sense that maybe if we solve the problem, we can guess that first, if we consider all technologies together, so it would be cost effective to go for hydro first, and if technical limits let us, we can use and install mini hydro as much as the problem let us to do it. Otherwise, if we face, for example, technical limits or other constraints in the network, we need to choose other technologies. And here we have fuel costs. This index is 1, 2, 3 that I told you, I showed you here. Fuel cost index 1, 2, 3. Now we use it here. 1, 2, 3. The first one, which is the utility, we don't consider it. And another one is the diesel generator, and another one it would be hydrogen. If you would like to add hydrogen into your model, you need to give them another values to use it in your problem. And another technical limitation that we can have in our problem is maximum installation capacity. It shows us, the constraint on the installation of the technologies. We have used, large numbers to show that, for example, if we don't have that much limitation or technical constraints on technologies, which one would be cheaper to be installed. However, after that, I will show you, for example, if we bind them and limit the capacity of the cheapest technology, other technologies should be invested and be used to support the electricity of customers in the microgrid. So this one shows the utility or transformer capacity, 300 kilowatt. And we have diesel, pumped hydro, and all these technologies. However, another constraint which is important for us is maximum build rate in each year. So it means that, for example, in each year, we cannot install more than 500 kilowatts of battery. The cap for it is, for example, 500 to 1,000. However, depending on your problem that you might have in the future, you can change them and manipulate them. And these are the reliability factors that have been considered for the network. We can see that battery, mini hydro, pump hydro, and diesel and hydrogen, we call them firm generation because they don't have that much uncertainty. They are more reliable than wind and solar because they are volatile, wind speed or solar irradiation, they are changing all the time. That is why we have used these factors for them to consider in our problem. If we would like to address the emergency loads, we need to consider these factors for them, because if we want to support emergency loads, we need more reliable technologies. And this is a maximum load factor that you can select it and change it. Capacity factor, load factor. Here we have used the load factor for, again, renewable energy sources, and the load factor for reliable technologies, it is equal to 1. And we have give them these values. However, you can change them based on the type of technologies that you would like to use. And another important parameter is capital recovery factor, or CPI rate, we call it, discount rate, when you want to calculate the total planning cost. You need to consider the discount rate, because it is important when you want to calculate the net present value of the planning that you would like to do. Therefore, we need to consider this one, and for each year we have calculated them. I'm not sure if you are familiar how to calculate the capital recovery factor, because it is important when we want to calculate the planning cost and capital cost, and we need to use the net present value. Actually, it shows the worth of your money that you will invest, for example, in 2028 at the current year. And the formula is like 1 divided by 1 plus the discount rate power the lifetime of the project. And absolutely for each year it will be changed. As you can see, this is constant. This value is constant, and the reference year is 2022, and for each year we need to calculate the CPI, or capital recovery factor, until the end, and we need to multiply it by the planning cost in each year. So now that now you know that what types of input parameters you need, do you have any question regarding the different types of input parameters that
No,
I
Abbas,
explained to
they
you?
don't have any question. Please continue.
So if you don't have any questions, I will go to the codes. You need to open the main file. If you double click on the main file, you can see the MATLAB M file that we have developed already. This syntax is for clearing your previous results in MATLAB, or closing all figures that you have produced already. So now we would like to read the input data, the Excel file. So we have defined Excel, so we need to give it the directory of our input file. So in your code, this address is different. You need to change it. What you need to do is that click on this directory, copy, and paste it before this /input data.xlsx. Input data xlsx shows the name of the input data, the name of this file. And we have already prepared an output file for you, you need to keep it as it is. I'm trying to open it. Anyway, this is your output file. And here we need to define the directory of our output file. And we need to again copy this one and paste behind the slash output.xlsx. It depends on the directory of the folder that you put it in your PC. So now we are defining our problem and model. We want to do the planning for the next 25 years. So we use this parameter, duration.nyear. This is the number of year. I gave it 25. So this one shows the planning years. And here I have defined, in addition to years, we need to define, the time bucket or snapshots of our operation. So as we said, we considered 4 seasons or quarters, and we have considered 1 day, 24 hours as a representative of this month. Therefore, it means that we need to multiply the whole year, which is 25 years, by 4 quarters by 24 hours. So this one shows the total planning hours, which are different, they are they have a different characteristics. You could also multiply it by, for example, 30 to show it every month, for example, and multiply it by 3 to show, for example, 3 months in each season. It depends on how you model your problem. So the number of different period, so is equal to the number of years multiplied by 4 quarters that we have, as you can see. And in this coding, we have used to show that, for example, each time bucket is related to each year. Therefore, maybe I will run it for you to see what will happen. What, for example, year in time bucket shows for us. I run it. You can also run it yourself. Select this part and do the run. Select the button, run button. only run this section. Okay, if we go to the duration structure, duration is the structure
Hello.
in MATLAB that includes several different parameters, number of year, time bucket, and so forth.
Sir, I have
This
one
is the
doubt.
workspace here. If we click on the duration,
Abbas, there is a question. So,
we can see n year and
Abbas,
time
can you hear
bucket
us?
and period.
Hello. Sir, I have one doubt.
This is equal to 2,400. The number of operational snapshots that we have. And this one is the number of period for multiplied by 25 years. And this one shows years in time bucket. So as you can see, the first 24 hours, they are 1, 1. So it should be 1 until
Hi, Abbas.
48. Yes.
I think they have got a question. So, can you just wait? I mean,
Yeah.
you can try now. Use the microphone.
Hello.
Hello.
Yes, we run the .m file from line number 1 to 11. That's the error. We found that error in get solver.
Oh, yeah, because
Yes, yes. The error is that
I think
error in get solvers, line number 3.
Problem with the solver.
Solvers, right, right.
Have you installed solver?
No, I think we didn't.
No, if you don't install solver, then you
No.
won't be able to run it.
Means, sir, how to just get this? How to get this solver?
I mean, you need to install that solver.
can you type
So can you tell us
Yeah.
once again how to get
yeah,
this?
can you write this code in the command window, yalmip test? Can you tell me if it works or you will receive any error?
Is it working? That one? Yeah, we have to download. So I already sent an email.
It is easy. You know, you need to go to the Yalmip website. Yes. Just Google it. Yalmip. Click. You can see here Yalmip. Click on it. You will be directed to the website and click on the download. Latest release. Click on this one. And it will be downloaded. Downloads. Yalmip. It is a zip file. Please extract it. Then you have this one. Then copy it. Make a copy of it. Copy. And then go to the path that you have installed your MATLAB file. It is C. Go to your drive C. Program files. find MATLAB. Click on the MATLAB, select the version of your MATLAB that you have installed on your desktop, and then you need to find Toolbox. Click on the Toolbox and paste it here. You should have this file, GIAN Master, in the Toolbox folder. So after you paste it here, you need to copy again this directory, copy this one, and get back to your MATLAB. In the home, and go to the set path. Select set path and add with subfolders and paste it. And then select GIAN MIP and then select folder. You will have it installed. And then to see if your installation has been successful or not, just type GIAN MIP test. It gives you all information about the solvers. For example, these solvers have not been installed. However, we don't use these solvers that are not installed. Our some solvers, they have been installed already. And if you press any key, it will solve a problem for you. An example.
Is it okay now? Is it okay? Have you followed that step? Yes, Abbas, please continue.
Okay. So again, repeat it, select these sections and go to the editor, run section. You should receive this output in your workspace. Duration out LX. If you open the duration, it consists of the parameters that we have defined. How we define a structure, for example, for duration, we need to put dot. If you are not familiar with, for example, like a structure or anything, you can search easily in MATLAB. Here, or also when you double click, you can click on structure. It directs you to the instruction for extract. This is an example. For example, we have defined two different parameters, A and B for S. Everything is fine?
Yeah, please. I think all good.
Okay. So here I wanted to show a year in time bucket that we have defined. As you can see, it includes one row and 2,400 columns. And it shows that each column is related to, or each time is related to and corresponds to the each year. So because we have defined 4 seasons and we have 24 hours, if we multiply it 24 by 4 after 96 columns, we see that we will see year 2. This one is year 2, year 1 until the 96 time bucket or hours. And again, after the next 96 time bucket, we see year 3 until the end to go to 25. As you can see, 2,400 columns and 25 years. So what syntax we have used to show like a matrix for us for the year in time bucket, we have used the repeat, this syntax rep math. What does it do? It is repeating each matrix, for example, by 20 by 4 times 24 colon. If I run it, you can see it. So this syntax is doing like this for us. It is repeating all rows. 96. We have defined that matrix. And if we want to return it and change it to only one array with one row, we need to use this syntax, reshape. Reshape it. We have used only one row, and we put empty in the columns. And we will do the same for duration in period. Here in period, if we go to that, we can see that we have 100 periods, 4 seasons multiplied by 25, and we want to see each period corresponds to each year. It depends on how you are doing the programming. Maybe you can use different ways or more efficient ways to do the programming. So now that we define the input directory, output directory, we have defined some parameters, and at the moment we need to import the input data. To import the data, input data, we have defined a function, and we call it input is equal to this function, and it has 2 arguments, XL and duration. Duration we have defined it here, and XL is the directory. So what this line does for us is that it goes to this function, which have written it in another M file. You can open it, import XLS. This is the function that we have produced. As you can see, the function is returning a parameter. We call it output. Output is actually this input. When it comes out of this function, they will be saved in the input parameter that we have defined. However, in this function, this is import XLS. This is X or XL that we have defined it, and duration. So now it is time to read the data from Excel. We need to use this syntax, XLS read, and it will go to the GIAN. This is the name of the sheet, as you can see. XLS read file name, which is XL. XL is the directory, this directory. And we have selected B3 to Q10. If we can see that B3, it starts from here. It selects this B3 to Q10. So it will select all this table for us. And we need to extract it in this format, and then we give the generator names or the name of each technology like this. And to define the number of generator, we use length.
Abbas,
Yes,
so they need like 10 minutes break. So you can stay online, but
Okay.
just wait maybe 10 minutes and then probably
sure.
we're gonna finish by your time 9.
Okay. 9? Okay. After break, we will get back. I will
Yeah.
get back in,
You can have a
Uh,
break for 10 minutes and you can
eight-
come.
yes,
can come back.
8:30, I will get back. Yeah.
Hi, Abbas.
Yes, I was here. I was waiting for
Okay,
you
please
to.
start.
Okay. Can you see my screen?
Yes. All good. Please continue.
Yeah. And then after we read this table from our Excel sheet, again, we will define the parameters in MATLAB, and we will define them using these syntaxes. Again, fixed variable fuel cost, maximum install capacity, the construction rate, reliability, load factor, discharging efficiency rate, and charging efficiency rate, and the energy storage system charging rate. And this one is CPI. It goes to the another sheet in Excel, and it will read it for us. And again, we will go to the variable cost sheet to extract the data, and here is operation and maintenance fixed cost, and this one is the total capital cost for technologies. And fuel cost, we will read every table in our Excel sheet. As you can see, we have considered the CPI in our capital cost because we want to multiply it by the size of technologies. Maximum installed capacity, maximum build rate. It is again another sheet in Excel. Reliability factor, capacity factor, load factor, and the demand data and renewable energy sources parameters, solar pattern, wind pattern, as you can see. And here we have defined a list for our energy storage systems. We put these numbers in the array that we have defined, 3 and 6. 3 is the index for battery energy storage systems, and 6 is the index for pumped hydro storage. Here you can see 3 and 6. Sorry. 3 and 6, pumped hydro and battery. And again, we write some codes to make a difference between solar generation, wind turbines, energy storage system, as well as the utility. We want to define them another index, and we are defining dispatchable list or firm list, as well as the variable renewable energy sources list, that it includes energy storage system, solar, PV, and also utility list, as well as the hydro. And here we extract and define our tariff data, feed-in tariff data, as well as the consumption tariff data. And again, we can see that because we need to calculate the operational cost and how much electricity we need to sell to the grid. Again, we need to use CPI. You only need to go to the formulation of how we need to minimize the planning costs. So in this function, we have read and define all input parameters, and then we return them, return all the input parameters, put it into output, and return it to the input here. And the scenario is scenario number 1 in the load. Here, we have considered this scenario. It is a base load. In that project, we have two different scenarios, base load and high demand. Which one? This one is scenario 1, another one was scenario 2. However, we have models, other scenarios as well to show in a better way that how our result can be affected by uncertainty of demand. So next step in this toolbox, we need to define all variables, and not all variables such as total cost, absolutely only decision variables, because we can calculate costs from, if we have decision variables, is like, you know, the output of each technology, the output power generation of each technology, or for example, what is the optimal size of each technology. These are the decision variables. Then from them we can calculate, for example, the costs. Although cost is variable, however, it's not a decision variable. It is dependent on decision variables. So we need to use this syntax, this function, get solvers. If we go to get solvers, it is another function with the arguments of input and again duration. Inputs, we have defined it here, and duration is here. Again, we bring it to this function. So we need to open get solvers. This is the function that we have defined. So when we want to define the decision variables, as I showed you on the website, we need to use this term, SDPVAR. And this one shows the dimension of our variable. For example, number of generation, number of generators, and the time bucket that we have. And this one shows the output for sizing, installation of each technology, in each year, it shows us. And this one is the capacity built in each year. This one shows the cumulated installation for each technology. And here we have the charging and discharging for our energy storage system. We have used ESS list that incorporates both battery and pumped hydro. And we need to calculate, for example, the initial SOC. Sometimes in problems, in order to prevent the complexity of the problem, sometimes we give them the initial value. However, in this problem, we have supposed that it is a variable, and this one shows the total SOC, state of charging, for each technology, and this one shows the output of each generator in the problem. So we have defined all decision variables here. So we will get back to the main function. Next one is next step is to define constraint. And to define constraint, we use this function. Again, however, this time this function is dependent on decision variables input as well as the duration that we have considered there. So we need to open get constraint function that we have defined. So we will define it using this syntax, constraint, and for construction, for example, all the constraints that we have, we need to model them in our problem. For example, the maximum limitation of building technologies, we need to consider this constraint. For example, the maximum build capacity, build rate, it should be less than equal to, for example, that input parameter that we have assumed already. And here we have operational constraint and modeling for different technologies, solar, wind, and other technologies. These are dispatchable dispatching constraints that we have considered for them. Or some of them is related to the capacity of each technology that they can produce. Or we have considered the ramp-up rate for dispatchable technologies that we have considered. And here we have model energy storage system constraint, initial SOC, which should be between the minimum SOC that we have considered 0, as well as the maximum capacity that we have modeled it in this problem. And this one calculate the whole SOC, charging and discharging, we need to add them, which are multiplied by efficiency as well. Here you can see each SOC is equal to initial SOC minus the discharging rate minus charging rate, as well as the discharge plus discharging rate to calculate the SOC and model it for us. So next step is, after modeling the energy storage system, this one is for the last hour, the initial hour, after we can calculate them. And we need to model the power balance equation. Summation of generation is equal to summation of load. Generator output, as you can see, is equal to our load, input demand. So after defining all constraints, again, it returns const parameter into these constraints for us. And then we need to define our objective function. Variable operation and maintenance costs, fixed operation and maintenance costs, we need to calculate them. So we need to sum up the variation as well as the fixed operation and maintenance costs, as you can see, to show the whole operation and maintenance costs. And here again, we have defined different distributed generation lists, solar, wind, and dispatchable, as well as energy storage systems. Here, in order to linearize our problem, we multiply them by 0.5. This is an approach to linearize the problem. And we have calculated, feed-in tariff. The total operational cost is the amount of electricity that we buy from the grid, as well as, minus the amount of electricity that we sell to the grid. So these are the operational costs, or also the fuel cost. We need to consider them as well. This one shows the utility cost, the electricity that's selling to the grid, or which is buying from the grid. This is our utility cost, and this one, which is an objective function, is summation of all capital costs as well as the utility cost plus operational costs. As you can see, we have considered all of them. And next step is to define the settings for our optimization problems. At this stage, I disable these lines because you don't have Cplex installed in your PC. We would like to use this solver instead of Cplex. If you don't write this syntax line,
Abbas,
that is, yes,
sorry, just finish maybe within 5-6 minutes, okay?
sure. So it is all done. It shows how we can choose the settings for the solver. And then this syntax is important, optimize. It is a built-in function in this toolbox. And we need to write constraints that we have defined, constraints, and objective, and the settings that we have defined, option that we have defined for the solver. And this code shows us we did some analysis after solving the problem. So until this line, it will solve the problem for us. However, after that, maybe you need to do some more analysis or export your results to the Excel. So I need to run it. You can also run it on your system. Takes time. As you can see, it shows busy. So now it has been solved. As you can see, we can see different outputs here. You need to go to the info. You can see successfully solved. So it is feasible, and then we can calculate other parameters that we need, such as, for example, levelized cost of energy or utility cost. Or, for example, here we can see the objective is negative because it took some it was the beneficial for the utility because it was selling electricity to the grid. That is why it is minus. However, at your home, you can manipulate these parameters. For example, you can change the amount of the capacity of technologies. For example, maximum capacity. For example, for mini hydro, you need to suppose it is the maximum sizing limitation that you have is 400. So you need to close it and reopen it, which it doesn't work. However, you need to change this number. For example, set the value of 400 and copy and paste all the columns for all years. Then run your program and compare your results to, for example, what will happen to the levelized cost of energy. And this one, we have also developed a tool for this microgrid. As you can see here, we have developed a dashboard incorporating, different functionality, how we can calculate the cost-benefit analysis, how we can do the investment planning or
Boss.
forecasting. Yes.
So this one, I'm going to show it tomorrow because the time has
Okay.
already passed. So anyway, thanks for your time.
No worries. No. If you have any question, you can reach to me. And,
Okay, no, thank you.
I will
So
happy
I
to
mean,
answer. No worries.
as you see, this is like the modeling optimization. So definitely, I mean, it's gonna be taking time. 2 hours is not enough. But I think you have got the code, right? And MATLAB is very self-explanatory. I mean, if you don't understand any function, just write help, and then it's gonna give you all the detailed description. So yeah, so I think you have the code. Please, you can try with any input. Data you might have, and then this code gonna give you the optimal design for microgrid for any application. Thank you.
Thank you. Thank you. Have a good day.
Okay, Abbas, you can leave. Thank you.
Okay, bye.